My invisible friends, hello and welcome back to our series on electrical and computer engineering. Today we have our third video on a small series dedicated to electric and electronic filters. It is about time we start talking about active filters. We begin with the inverting amplifier, the one we saw last term, two resistors, R1 and R2 and an op-amp. In that one, let's remember how it was that we would find the transfer function of such an amplifier. Look, the voltage here is 0 volts. Why? Because the op-amp is guaranteeing that Vn and Vp are the same, and Vp has been solidly grounded, so that voltage is 0 as well. We apply voltage V1, the current in the R1 resistor has to be V1 minus 0 divided by R1, that is the current through that resistor. Because the input current to the op-amp is 0, it always is, then that current has to continue flowing through the other resistor. The other resistor, R2, sees the combination of R1 and the op-amp as a current source. That is an implementation of a current source. R2 has no say on the value of that current. The current is whatever it is, V1 over R1, but that current will produce a voltage drop in R2 with this polarity, and the value will be given by Ohm's law, which is Ri, R2 multiplied by V1 over R1. That is that voltage. Because the voltage on the left of R2 is 0, then the voltage on the right, which is V0, the output voltage, has to be negative that voltage. So that is the output voltage, negative R2 over R1 multiplied by V1. If we divide the output by the input, we get the transfer function that we used to call that the gain of the amplifier. V0 over V1 is negative R2 over R1. And that was fine. That was an inverting amplifier. But what if, and now that we know that that is true, we substitute R1 and R2 by two full-blown impedances, Z1 of S and Z2 of S. Then the transfer function will depend on Z2 and Z1. Theoretically, we can achieve any transfer function that we want this way. One op-amp, two impedances, and we're in business. This idea caught the imagination of many researchers in the 1950s, and in 1955, two researchers working with the MIT Lincoln Laboratory, R.P. Sallen and E.L. came out with a topology that has become the workhorse of electronic filters. This one, the Sallen-Key topology. I invite you to find the transfer function of that topology, and it's given like that. However, each one of those impedances, Z1, Z2, Z3, and Z4, they can either be one resistor or one capacitor. In particular, they came out with this topology that is a Sallen-Key low-pass filter, and its companion, the Sallen-Key high-pass filter. The beauty of those topologies is that they allow us to set the poles of the transfer function anywhere on the left-hand side of the complex plane. Why would we want to do that? Or we shall see that later when we study Butterworth filters and perhaps Chebyshev filters. But the beauty of that is possible because the Sallen-Key configuration allow us to set the poles anywhere on the left-hand side of the complex plane that we want by choosing the right values of R1, R2, C1, and C2. We will see how that is done. I insist, with the Sallen-Key topology, we can locate the poles where we want. Let's say that we want that the poles are at -3 plus J4 and -3 negative J4 complex conjugates. If the resistors are given, they are 1 ohm resistor, each one of them, and we have a low-pass Sallen-Key topology, what should be the values of C1 and C2 in the Sallen-Key configuration? What should they have? Let's go to the whiteboard. In the whiteboard, we see the Sallen-Key low-pass configuration. The resistors are 1 ohm. The capacitors C1 and C2 are unknown so far. I want a transfer function, and for that, we apply a delta of Dirac in the Laplace domain. That is 1. And the impedances for the capacitors are 1 over C1S and 1 over C2S. Let me identify the currents IA, IB, IC, and ID, and then we can write a KCL equation for node 1 here, and another KCL equation for this other node here at the non-inverting terminal of the op-amp. In the calculator, I define the values of the currents IA. IA is 1 minus V1 divided by 1 ohm. That is the current IA, 1 minus V1. IB is V1 minus V0 divided by the impedance 1 over SC1. That is SC1 multiplied by V1 minus V0. The current IC is V1 minus V0 divided by 1 over here. And the current ID. ID is a reserved word in the HB prime, so I call that IDD. ID is just V0 divided by the impedance, 1 over SC2. So that is SC2 V0. And we can write the KCL equations for node 1. IA is equal to IB plus IC. Check it out. And for the other node, IC is equal to IDD. Solve the two equations for the two voltages V1 and V0. And we're interested in V0 because V0 will be h of s transfer function. We have seen that. When we apply an impulse here, the output is directly the transfer function. So this is a transfer function. However, we are used to having that the coefficient of the quadratic term is 1. So we need to divide numerator and denominator by C1, C2. So we have the canonical form of that term. Let's come back here. That is a transfer function of that filter. Just like that. You say, okay, that is okay. How are you going to find the values for C1 and C2? Let's remember something. The poles, where are the poles? They are at -3 plus J4, and -3, -4. Let me draw them here in real time. This distance is what we call the undamped frequency associated with that pair of poles. And the cosine of this angle is the damping factor. But that hypotenuse, if this side is 3 and this side is 4, that hypotenuse is 5. So omega naught, the undamped frequency, is 5. And this cosine, you remember, SOHCAHTOA would be 3 divided by 5. That cosine, which is no other than the damping factor, will be 0.6. So we know what is omega naught, 5, and we know what is the damping factor, 0.6. Why do we care about that? Because we remember from the body plot that a trinomial like this one, produced by a pair of complex conjugate poles like the ones we have, it is written normally in control theory this way: s squared plus 2 times the damping factor omega naught s plus omega naught squared. But we know omega naught when we know psi, so that translates into that polynomial should be s plus, say, 6s plus 25. You see where we're going with this? We know now that this term has to be 25. That is one equation. And we know that 2 over C1 has to be equal to 6. Has to be equal to 6. Two equations, two unknowns. Let me write them down here. 2 over C1 has to be equal to 6. From that, we solve for 6. And 1 over C1, C2, that has to be equal to 25. From there, we find C2. And that is how you do that. What I said, with a Sallen-Key configuration, we can put the poles of the transfer function anywhere we want on the left-hand side of the complex plane. We don't know why that is useful yet, but we have that power. Another example of Sallen-Key filters. I let you work on this one. What type of filter is this one? Yes, I know that I've already told you this is a low-pass filter, and I give you the values for the resistors, 10 kilo ohms each, and the capacitors, 141 microfarads and 70 microfarads. The question is, it's a low-pass, right? So what is the corner frequency of this filter? Let's talk about filters and the relationship of their behavior with the location of the poles of the transfer function. We have seen how the poles of the transfer function, that is the roots of the denominator of the transfer function, are decisive in determining the behavior of a filter. What about the zeros? They have some saying too. Locating the poles, the roots of the denominator, in convenient places, we will see what we mean by convenient later, of the complex plane can result in desirable frequency responses. In particular, there are two families of polynomials for the denominators present today in filters. Those are the Butterworth polynomials and the Chebyshev polynomials. Butterworth versus Chebyshev filters. Butterworth filters, after the English engineer and physicist Stephen Butterworth. Those have a flatter frequency response in the passband, but they are not so steep in their cutoff characteristics as, let's say, Chebyshev filters. Chebyshev filters, after the Russian mathematician Pafnuty Chebyshev, they have a very steep cutting slope right after the edge of the passband, but they tend to overshoot near the cutoff frequency and they are wavy in the passband. Bessel filters, we will study them in third year. Let's look them up on Wikipedia for your own reading enjoyment during the summer. I invite you. Wikipedia has fine articles on each one of them. Butterworth filters, that is filters that have a Butterworth polynomial in the denominator. They have a flatter response in its passband. They have less ripple, but their transition band is not as steep as, let's say, that of the Chebyshev filter that we will not study in this video. Look, there you see the Butterworth filter responses, and in the passband they are smoothly flat, and you see the transition bands. For the corresponding Chebyshev filter, order 4, in this case, you see that the exit slope of the fourth order will be, given by that line, will be whatever it is, but at the very beginning, right after the edge of the passband, the slope is steeper than the order of the filter, so it's steeper than the slope of a Butterworth filter. So that's why it decays faster. That is a characteristic of a Chebyshev filter. How he achieves that, well, we will cover that in a separate video, none of this series. Let's refresh our memory on what is the impact on the body plot of the presence of two complex conjugate poles, one at A plus JB and another at A minus JB. This is something that we show in body plots. I'm just repeating that. Those two binomials, when we multiply them, we get a trinomial like this one. But in control theory, we prefer to write that trinomial this way, S squared plus 2 times psi omega naught S plus omega naught squared. Omega naught who? The undamped frequency of the transfer function. By the way, that's where in the body plot we will have one corner in the contribution. And where's the other one? That's psi. Psi is the damping factor. What is with them? So omega naught tells us where will be the corner of the contribution of that trinomial. And psi tells us how much of an overshoot we will actually get in the detailed response. Let's have a look at that. A trinomial like that contributes with curves like the blue ones over here. So the approximate contribution will be given in the body plot by the red lines like that at the corner frequency, omega naught the undamped frequency, in this case 100 radians per second. But observe, for very small values of the damping factor psi, the actual curve has a big overshoot. But for big values of psi, closer to 1, which is the maximum value of psi, then the overshoot is negative. That gave possibly Butterworth the idea of combining some parallel poles with positive overshoot with some other poles with negative overshoot so that they would cancel the overshoot near the corner and have a much smoother response for the filter. That was genius, all right? So all the poles, they contribute with the same corner. So they have to have the same omega naught. They have to be at the same distance from the origin, but they will have different damping factors. Let's go back to the complex plane. In here, we see that omega naught is the square root of a squared plus b squared, equating those two trinomials. And of course, doing the same, we say psi omega naught has to be equal to A. Graphically on the complex plane, we see those two poles at A, JB, and A negative JB. A, of course, is a negative number. Omega naught, we've said, is that the Pythagoras um, um, computation. Omega naught is the square root of a squared plus b squared. It is that distance. It is the absolute value of the pole, if you have to know. And who is psi? Well, look at the second equation. Psi omega naught is A. So psi is A omega naught. Remember SOHCAHTOA? That means that psi is the cosine of the angle zeta there in that figure. A divided by omega naught, that is that cosine. That angle zeta, by the way, is pi minus the argument of the pole. So the damping factor can be computed on the calculator as the cosine of pi minus the argument of the pole p. Fine. Let's say that the poles are at -3 plus j4 and -3 negative j4, and we want to find what is the undamped frequency, what is the corner in the body plot, and we also want to know what is the damping factor and what is the quadratic term. Yeah. How does that trinomial look like for that pair of poles? With a calculator, I define the pole P as -3 plus j4. The absolute value is omega naught, that is 5. That's going to be the corner on the approximated body plot for the amplitude. Psi, the damping factor, is the cosine of pi minus the argument of p, that is 0.6. So the coefficients of the trinomial are 2 psi omega naught. We've seen that. So 2 psi omega naught, that's going to be 6. And omega naught squared, that is the independent term, that is 25. So that trinomial has to be s squared plus 6x plus 25. Let's talk a little bit about Butterworth filters. An introduction. Butterworth chooses all his poles at the same distance from the origin and at the same angular distance from one another. Why he does that, I've already told you, because that way all of them contribute with the same corner on the body plot. But given that they have different damping factors, some of them have positive overshoot, the others negative overshoot, and then they add them up, they cancel out the overshoots and gives you a very flat response. That is a blend of Butterworth. Look, here you have 4 such Butterworth poles. They are all at the same distance from the origin, so they contribute with the same corner on the body plot. That's why they are on a circumference. The radius of the circumference will be omega naught. That will be the corner frequency on the body plot. That is omega naught, all right? That is omega naught. The radius, that is the corner of the body plot. But they are at the same distance from one another, which would be pi divided by number of poles, pi over 4, that is 45 degrees, and 45 and 45. And the rest of the pi radians, well, we go half of 45 at the top, half of 45 at the bottom. By the way, you notice here that the pair P1, P2, they have a very small damping factor, so they will contribute with a big overshoot. While P3 and P4, they have a very big damping factor, so they contribute with a negative overshoot. They will cancel out the overshoots and give you a very flat response. There are formulas associated with Butterworth filters that we will not be using in this course, but I want you to know them anyway. This one, omega naught, is the corner frequency on the body plot, and omega p. You know what is omega p, we've seen that in previous videos. Omega p is the edge of the pass band. They are not exactly the same, but in this course we'll approximating for Butterworth filters as being the same. The small difference depends on epsilon, and epsilon depends on A max. Who was A max? Remember the previous video? Was A max was the maximum tolerated variation of the attenuation of the transfer function in the passband. That was A max, 1.5, 1 decibels, 2 decibels, 2.5, 3 decibels. Depending on that, when you tolerate, you get a different epsilon, and with epsilon and n, which is the number of poles of the filter, you get the relationship between the corner frequency omega naught and the edge of the passband omega p. In this course, we will assume they are the same. Here are a few maps of poles for Butterworth filters to get familiar with them. For n poles, they are separated by pi over n, and for 2 poles, they are separated by pi over 2, that is 90 degrees. For 3 poles, pi over 3, that is 60 degrees. And pi over 4, 45. We've seen that already. Pi over 9. And the formulas that I mentioned before. Here's an exercise in Butterworth filter. In this case, they give us the Butterworth filter. A passive Butterworth filter of order 4. Is it or is it not? Check it. How? Find the transfer function, find the poles. They must be at the same distance from the origin. All of them must have the same absolute value. And then check that they are at the same angular distance from one another. 4 poles, they should be away 45 degrees from each of its neighbors. Correct? If that is true, this is indeed a Butterworth filter of order 4. It is passive because it has no op-amps in it. Another example. We've done something like this already, so it's going to be easy. An active low-pass filter, Butterworth type, of second order is taken from a filter's codebook. The corner frequency is 1 radians per second. Omega naught is 1. The resistors are 1 ohm each. What should be the values of capacitors C1 and C2 in farads? Well, if this is a Butterworth filter and it's order 2, we already know that what is the location of the poles. You say, how is that? Well, the corner frequency is 1, so that means that on the complex plane, allow me, they are at a distance of 1 from the origin. All right? 1, 1 and 1. And the angle here is a pi divided by 2. This is 90 degrees, so that means this is 45 degrees. So that means that the damping factor is the cosine of 45 degrees, which is root 2 over 2. So we know omega naught is 1, and the damping factor is that. So you can write your polynomial s squared plus 2 times psi omega naught plus omega naught squared. You know what that is, right? So replace this one, and you get s squared plus 2 cancels 2. This is root 2 s plus 1. That is 1. And you remember that the polynomial was something like this. I don't quite remember. I think it was C2s plus 1 over C1, C2. Remember that one? 2 equations, 2 unknowns, and you find C1 and C2. Piece of cake. Here's another example. But in this example, I give you the values of all the terms, the parameters, and I ask you to check that this is indeed a Butterworth filter. Thank you very much, my invisible friends, and I hope to meet with you again in our next and final video on filters and introduction. Good night.